Good evening. So I wanted to make a few announcements before we get going. First thing is that I hope you are aware that after every lecture, I repost the syllabus with the link to the recording. Okay, I hope you are checking that out. I made a few changes in the course schedule, anticipating that I want to use more lecture periods for this topic, partial differential equations. I pushed exam 2 back by like a few days to November 4th. Exam 2 will be covering module 3 and 4. But before that, next Monday evening, you have your first exam covering modules 1 and 2, 4 problems, 80 minutes, 2 sheets of handwritten notes permitted. Okay, so that is covering modules 1 and 2. Your first project, for which I gave some instructions in the towards the start of the last lecture, is going to be due on October 30th. Previously, it was due on 28th. Just pushed it back by 2 days, which I assume nobody will complain about. Okay. I want to remind you about the grading scheme, which is pretty steep for this course. If you don't do well in even one exam, there is no possibility that you will get an A. That's how the course grading is set up. Okay, so I want you to prepare well and do well. This week in the afternoons, generally I am available between 1 to 3. So if you have questions, please feel free to come by my office. Except Friday. Friday I have faculty meeting, but other days of the week I should be around. You can look for me either in room 312B, 325, or 327. In one of these rooms, I can be found. Okay. All right. Any questions so far? Okay. So the other thing is related to attending class through Teams. Fall season is here. If you get sick, if you feel you could be potentially contagious, let me know. We'll work it out. Okay. And there could be some days in which I will be traveling. So I'll be teaching the class through Teams. So I'll let you know ahead of time. As of now, September 30th and October 2nd, those 2 lectures are likely to be through Teams. September 30th and October 2nd. Okay. I will, of course, give plenty of intimation through email, so you will have it in your inbox. Okay. As of now, it's likely that it will be through Teams. Okay, all that said, we can continue with our discussions. We are working through section 5.3 in the textbook, where we are looking at the Frobenius method. So section 5.3, Frobenius method. To review that, unlike the power series method which we saw earlier, the Frobenius method starts with the assumption that y of x is of the form x to the power r m from 0 to infinity am x power m, where r is any number or r is real or complex, and a naught is not equal to 0. These are this is the starting point of the Frobenius method. So we are looking for solutions to the equations of the form x squared y double prime plus y double prime plus d of x over x times y prime plus c of x over x squared times y equal to 0. This is generally the type of equations we are looking for solutions. Now, if the right hand side isn't 0, if it is some other function of x, is our strategy going to change drastically? You will end up at a point where you do comparing the coefficients. If the right hand side is a function of x, you know how to express it as a power series if it isn't already a polynomial. So you would still go through the same procedures. Okay, so I'm not discussing that case separately, assuming that you would be able to catch on. Okay, so we have this equation where b of x is an arbitrary function which could be expressed as a power series, as a known power series, and C of x is the same. Okay. For this equation, substituting y of x of this form, you will end up with what is called as the indicial equation, which is an equation of the form, the all important indicial equation to determine R would be R times R minus 1 plus B naught R plus C naught equal to 0. We saw three cases. Case 1, R1 and R2 are real and do not differ by an integer. I don't have to say real, I just have to say they are distinct. They could still be complex. Case 2, a double root wherein R1 equal to R2, and case 3, is R1 minus R2 is equal to an integer. And for each case, we saw how the form of the solution would look like. We did one example for case 1. I think we started an example for case 2, and now we need to wrap this up. Okay. Now, what we have emphasized in this is for you to follow a lookup table type approach, where you could do this from scratch every time if you know the underlying principles, which is okay. But to save time, what we are trying to do is to first express the PDE or so ODE of this form. Make sure that B of x and C of x are analytical at x equal to 0. First we ensure that write them of this form. Once you have them written down and express B of x and C of x as a power series, then you pick out B naught and C naught, evaluate or solve for R, and then come to this flowchart. Depending on which case your particular situation falls into, you would pick up the solution related to that case and express your power series. And this is given in theorem 2. That is in the textbook. This is given as theorem 2, page 182. So how to choose the basis functions for your solutions is given to you in theorem 2, page 182. And we'll pick up the second case today and continue. Before I do that, this method or the power series method, we have been seeing only through second order differential equations. If a situation presents itself with a third or higher order equation, how would you adapt yourself to that situation? Just tell me so that I can understand how you're thinking about it. Yeah.
Reduce the order.
Say it again.
Reduce the order of the equation to a system of equations.
You want to make this like two equations. That is one way to do that. But can you elaborate?
For example, when you are representing a system with the space state representation, you have a second order differential equation, and then you make it a couple of first order differential equations that you can solve.
Okay, so that would work for reducing second order to first order as is common in time domain problems, or even if you have a third order ODE or a fourth order ODE as it is common in bending problems, like in mechanics of materials. You could do that up to a while that you are able to reduce a third order to a second order plus first order. Sometimes it is much more beneficial if you start with this and you know your function is analytic at certain critical points which appear in the denominator. You could use this method directly on higher order equations as well, except you would have a higher order equation for the initial equation, third order maybe, let's say. And then instead of this flowchart, you just have to work out your own flowchart and generate basis functions. The whole exercise of generating solutions to ODEs is to identify basis functions. If you can do that step correctly, the rest is just working out the algebra. Okay, so think about how you will get an initial equation which could be a cubic, how to select three basis functions which are linearly independent, and then work out the remaining steps. Okay, this is just some general advice. Okay, so let's do example 2 in page 183. That is our example to illustrate case 2. Example 2, page 183. So we have, I think we started on this, x times x minus 1 y double prime plus 3x minus 1 times y prime plus y equal to 0. If I were to write it in this form, I would have y double prime plus 3x minus 1 divided by x times x minus 1 y prime plus 1 over x times x minus 1 times y equal to 0. And I would like to have a x squared to recognize the remaining as c of x. So I'll write this as x squared times x. So b of x is 3x minus 1 divided by x minus 1, which we wrote as a power series. Can anyone look in your notebook and tell me? We wrote this as a power series towards the end of last lecture. If you look in your notebook, this should be sitting there.
This is one of those quantity 1 minus 3x and then quantity 1 plus x.
Yep. So this is 1 minus 3x times 1 minus x to the power minus 1. Is this? Do you have it?
1 minus 2x squared minus 2x cubed.
Minus 2x minus 2x squared minus 2x cubed and so on. Okay, thank you. And then, so that means b naught is equal to 1. B naught equal to 1. And c of x is x over 1 minus x, or this is minus x times 1 minus x to the power minus 1, which would be minus x squared minus x cubed minus x to the 4th and so on up to infinity, which makes c naught equal to 0. Yeah.
Why, I was just wondering why you put the negative in front of the x and negative
Oh.
x and the c of x.
Yeah, force of habit. I did that once and I thought it needed that. So, sorry?
It was x upon square of x minus 1. You will take negative sign common. It will be
Oh, yeah. Thank you. That is why I had done that. So I have 1 x minus 1. I wrote that as 1 minus x. So I should have added the negative sign here, which will make it clear. I missed the negative sign in the intermediate step. So you have your B naught and C naught, which will allow you to construct your initial equation R times R minus 1 plus r equal to 0, which gives r squared equal to 0 or r equal to 0, 0, which points to case 2. Did you all see the mock exam I posted? Forgot to mention about that. So if you go to your Canvas and see under exam prep materials, there is a mock exam that I've posted for you to practice. Okay, similar to the format. Yeah.
I have a question. I didn't understand the question number 2.
Do you think shall we stop what we are doing and continue with
No,
that?
just the statement. It just was like, it's a very short statement, so it's
Okay, so yeah, you need to prove that. Show that j naught of x equals or j naught prime of x equals minus j1x. You have to prove that identity where j naught is Bessel functions. Okay, so you have this case, and I'll let you look up this theorem. The theorem is in a box in page 182, and tell me what are the two basis functions that you will select. Look at that table, write it down in your notebook, and then look up. So a couple of questions for you. You look at the table, this is your y1, one of the basis functions, and this is your y2, the other basis function. So we create y2 as taking y1, multiplying it by ln x to make sure it's linearly independent, and then add one more series to that. How would you obtain your coefficients? This is the key step. How would you get these a1, a0, which the problem boils down to this. You will have to reduce all of this to in terms of a0, so that it becomes one of your undetermined coefficients. And you need to reduce all of this in terms of a1 so that it becomes your other undetermined coefficient. You need to have two undetermined coefficients. Why? Why? Second order equation. Two pieces of information have to come from boundary conditions for you to evaluate them. No more, no less. You can't have 3 or 1. It has to be 2. Okay. So how do you get there?
y1 and y2x are the solution of the equation.
So you would substitute it in here and develop equations by equating the coefficients of x power m on both sides. Standard procedure, which we have done so far. This is where if the right hand side is another function of x, it's not a problem. It could be e power x or sine x. You know how to express those as a power series, right? The other day you asked about should you put logarithm of 1 plus x in your sheet. What I would put is Maclaurin series. If you know Maclaurin series, you can figure it out for any function on the go. That's what I would put. Okay. Shall we start?
Shall we have enough time to get the series?
Sorry?
Like if I just put Maclaurin series, let's say I have an idea series.
Yeah,
I may
okay.
not have enough time in the exam.
Okay, I would suggest putting common elementary functions. It also taking up space, and also Maclaurin series, and also know how to use the Maclaurin series if you need. You need to know all this. Remember, 4 problems, 80 minutes. So you'll have to clock in at like a 20-minute average. Okay, so when you are practicing, please time yourself to see if you can solve a problem in reasonably in 20 minutes. Okay. That is why the exam is supposed to measure your quick time response, and the project is supposed to measure your response when you get infinite time. So that you can then say, I took the time to think about it and here's what I've done. Some students, they are not exceptionally good at when they are under time pressure, but they are very good if they are given enough time. Some students are the other way. Some students are good at both. We come in all flavors. Okay, what's the next step? Shall we substitute y1 and then try to get the lowercase a0, a1, etc.? So we start with y1 of x is a solution, which implies I can go back to this equation, x times x minus 1 times y double prime plus 3x minus 1 times y prime plus y equal to 0. You can go back to this. Here's your, luckily for us here r is 0, so this is just the only equation. To be a little systematic about this, I would suggest you to get write this in this way: y1 a0 plus a1x plus a2x squared plus a3x cubed plus and so on up to infinity. Don't be lazy. That's what I'm trying to say. Y1 dash is a1 plus 2 a2x plus 3 a3 x squared and so on, 4 a4x cube and so on up to infinity. So I need y prime, which I already have. I also need xy prime, which is a1x plus 2 a2x squared plus 3 a3x cube and so on up to infinity. If you want, you could also have the x power m term. What will be this? This is what will be this? X power m.
n plus 1 am plus 1 x to the power.
M plus 1 am plus 1 x to the power m plus and so on up to infinity. And this would be m am x power m plus and so on up to infinity, because you are shifting to the right. You need y double prime, y1 double prime. That would be 2a2 plus 3 times 2 a3x plus 4 times 3 a4x squared plus 5 times 4 a5 x cubed plus and so on up to, what would that be? How do you generalize this formula here?
Plus 2 times m plus 1.
M plus 2 times m plus 1 times
A plus
am plus 2 m plus 2 x to the power m plus and so on up to infinity. and you also need x squared y double prime, which is shifting two places to the right. So that would be 2a2x squared plus 3 times 2a3x cubed plus and so on. Is this correct? Would you agree with me? What have I written here, is that correct? Yeah. Okay. Okay, so now next step. We want to put them together. X squared y double prime minus, oh, we also need xy prime, right? Also need xy prime, which is shift one place to the right, which is 2a2x plus 3 times 2a3x squared plus 4 times 3a4x cubed plus and so on. What would it be? Is this correct? What I've written as a term here. Okay, who can articulate how to get this just by looking at the terms and writing this? Who can give a give a trick to use? Can you tell me what's the process you are using?
You are multiplying with square term and subtract 2. So in the first term by double dash we have subtracted 2. So m plus 2 will be m and m plus 1 will be m minus 2.
Or in other words, you could take m, replace it with m minus 2. You will end up with m minus 2 plus 1 is m minus 1. M minus 2 plus 2 is m, and then you have x power. If you are shifting two places to the right, replace m with m minus 2. If you are shifting one place to the right, replace m with m minus 1. If you are shifting to the left, opposite. Replace m with m plus 1. Okay? This takes some, this is where you need some practice. Just if you do this and sit down and think about it calmly, you'll see it. Okay? Okay. We have this x y prime plus 3x y prime minus y prime plus y equal to 0. You don't have to, once you have written this down, once you have this like a table, you don't have to actually substitute and show everything in the same equation. You can directly skip over to saying, if you are like really feeling good about this and pro about this, you can say comparing the coefficients of x power m on both sides. If you want to go in steps, you could start by saying, let's say we do m equals 1. Actually, we can even start with m equals 0. Let's see what happens. We can start with m equals 0. What is? Can you write this down and then look up? We'll do this together. Are you getting this? So here is y, here is y1, here is xy1, which doesn't have a constant term, and then x squared y1, which also doesn't have a constant term, and then x squared y double prime and xy double prime. Would you agree with me? Yeah. So I'll have 0 minus 0 plus 3x, or 3 times 0 minus a1 plus a naught equal to 0, which is what I wrote here as a1 equals a naught. Okay. Then you can go for the next value of m. Where do I write? Right here. So let me check something. Renji, are you there? All right. M equals 1. Can you construct the equation, please? Am I doing it correctly? X squared y double prime doesn't have a x coefficient plus 0x that I did. And then I have xy double prime, which has minus 2a2. So this is x squared y double prime minus xy double prime plus 3xy prime plus 3a1 plus 3xy prime minus y prime minus 2a2 plus y. So we get the second relation, a2 is a1, which is a naught. Shall we attempt for just m, like arbitrary value, instead of m equals 2, 3 and so on? We'll skip ahead to m for any value of m, which would be x squared y double prime. I have this x squared y double prime m times m minus 1 times am, and then I have minus xy double prime minus m plus 1 times m a m plus 1 plus 3xy prime plus 3xy prime plus 3m am minus y prime minus m plus 1 am plus 1 plus y finally, plus y equal to 0 plus am equal to 0. So it involves am and am plus 1, current and next. So it's going to be a relation between am plus 1 and am.
So we have a 0.
We'll come to that. First, let's reduce that to write am plus 1 equal to something multiplied by am. Let's write that first. So please do that and then help me do this as well. So I have am plus 1 times m plus 1 plus m times m plus 1, or in other words, this is m plus 1 whole squared equal to everything with am is m times m minus 1 plus 3m plus 1, which is am m squared minus m plus 3m plus 1 is also m plus 1 whole squared, which gives me am plus 1 equals am. I never knew I was so good at math. Usually I goof up something. So we get, in general, everything is equal to, everything is equal to the previous value. And if you recall, we also got a1 equals a0, a2 equals a1, which fits in with this model. So your y1 of x simply boils down to a0 times 1 plus x squared plus and so on up to infinity, which you may recognize as a0 over 1 minus x. So that is one of our basis functions, a0 over 1 minus x. Can I erase this portion? This portion. So that means I would write y2 of x, the other basis function, to be y1 of x, which is a0 divided by 1 minus x ln x plus a1 x plus a2 x squared and so on up to infinity. So here on, the book is suggesting this approach. Let y2 of x be of the form u of x comma y1 of x, where u of x is a factor or a function that needs to be determined. Yes.
So, like when we assume this, like y2 is equal to y1 of x ln x and x function, so it's should like if the
I think you are asking should we include a0?
No, I'm asking like this ln x is every time for when the roots
Yeah.
of initial equation are same.
Yeah, this is the suggested basis function to generate two linearly independent bases. Remember when we did this for second order equations with constant coefficients, we said we'll take e power lambda x as one of the basis functions and just do x e power lambda x. We might as well have done x squared or other functions, but we said this is a acceptable basis functions. What will happen is when you write them as a solution, depending on what function you choose here, the value of the constants will correct themselves for it. So your boundary condition is the same. You might choose x e power x, I might choose x squared e power x. Our constants will differ for the same boundary conditions, depending on the basis functions. Okay? So to obtain the solution from here, the book is suggesting you to take y2 of this form, substitute back in the ODE to get an equation or a first order ODE for u and then solve for u. Okay, so this is solved as an example which is given in page 183, 184. To get the other function. And to conserve some time and to get started with Bessel functions sooner, I'm going to stop here and ask you to refer to the solution process in that example. Okay. I understand that we have like 2 modules and a lot of variability in the difficulty in questions that could be asked, which is why I posted a template to tell you what are the guardrails within which I will operate, like 4 problems, exactly on what topics. And I also gave you a mock exam for you to get a feel for how much difficulty to expect in those 80 minutes. Okay. So in spite of all this being very intellectually broad and everything, as far as the exam is concerned, I want to keep it narrow, keep it to those 4 questions or 4 topics that I have listed, to that level of difficulty. Okay, so let's not let your graduate education get in the way of getting a good grade. Yes.
Will you upload the example
Solution.
like on Friday maybe?
Yeah, sure. I'll try by Saturday night. I can't promise Friday. I have a lot of stuff on Friday. By Saturday night. So the third case is also given as example 3 in the same page, which I want you to attempt. Okay. Again, these are all pretty lengthy to try, so it requires considerable time investment on your side. Okay. Tomorrow, Wednesday, Thursday, these 3 days, approximately 1 to 3, I can be found. If you're coming, just shoot me an email before you come. Okay, so that I'll make sure I'm there. If not, I'll at least tell you come in 15 minutes, 20 minutes, something. Okay, so then we move on to section 5.4, Bessel's equation. Section 5.4, Bessel's equation. Okay, we are still going to use the Frobenius method, but we are going to apply it for a very specific type of differential equation, which is of the form x squared y double prime plus xy prime plus x squared minus mu squared times y equal to 0. Obviously, this is of the form y double prime plus y prime over x plus 1 minus mu squared over x squared times y, which if you compare with the equation from the last section, this says b of x equal to 1 and c of x equal to x squared minus mu squared. Which will make b naught equal to 1. And what is c naught? Minus mu squared. Right? So you can write the initial equation. That is, if you start with the Frobenius method or apply the Frobenius method for this problem, y of x equals x power r What is your initial equation? R times r minus 1 plus b naught r plus c naught equal to 0, which will get you r squared minus mu squared equal to 0, or r equals plus minus mu. Before I tell you the taxonomy of what mu could be and could not be and so on, can you try what possible cases are you looking at depending on what values this mu can take? If mu is a real number, go. Mu is some real number. Like I'm not saying like 0 or 1, not specifically an integer, but any real number. You'd have mu and minus mu.
Case 3.
Is this case 3? It could be case 1 or case 3, right?
It is still like 0 or 1.
Right. So their difference will be 2 nu.
Yes.
Okay. Say this is R1, this is R2. R1 minus R2 is 2 nu. Now this could be an integer or not. Like suppose mu is like 4.3. 4.3 minus 4.3, you get 8.6, which is clearly not an integer, which means it is case 1. So you know what basis functions to look up. Okay. You could have mu to be an integer, which could be like, let's say 2 and minus 2, which makes it 4. So this would be case 1. This would be case 3. And then you could have a special case where mu is 0, which would make this case 2. Right? Right? So you could have any possible case depending on what special constraints are imposed on mu. We'll start with mu is a real number. So you have two roots plus minus mu. Okay? If mu is a complex number, what happens? This is assuming mu is a real number. What happens if mu is complex? Case 1. So nu is complex. Let's say nu is of the form, say, I don't want to use R again, something like beta e power I theta. Just thinking through, okay, we are not going to immediately jump into this case. So nu squared would be beta squared e power 2I theta. Or actually, let's start with the more simpler. Nu is purely imaginary. Nu is purely imaginary. So I'll say nu is equal to I times z. I would have nu squared equals minus z squared. So I have r squared plus z squared equal to 0, or r equals plus minus iz. Right? R equals plus minus iz. So I could have, let's say, R1 is iz and R2 is minus iz. I'll just name them like that, which makes R1 minus R2 2iz. Now what? Which case does this fall into? Z is a real number now. Like, I mean, when I say iz, I mean z is a real number. So if z is any real number, even an integer, that still doesn't make R1 minus R2 an integer. Case 1. If z is 0, you are back in case 2. Right? Okay. So your main skill is looking at your modeling, arriving at the correct equation, identifying it as a Bessel's equation, and recognizing the new parameter to figure out what type of basis functions you are going to choose. If you got up to there, right, the remaining is the mechanics of the solution, which is more about doing it right and getting the steps right. Okay. Okay, so I just remembered one thing. Problem 1 in the mock exam is real simple. It will take us like 5 minutes to discuss it, which I can do next in the next lecture. Problem 2, I did that, and then I also admitted that this was the problem I had on the test and no more. You remember that? So it's in your notebook. Problem 2. Problem 4 is really simple. Like it's basically like saying d squared y over dx squared plus y equal to 0. You would almost tell me that the solution is a sine x plus b cos x. And you're asked to solve this using power series method. So you know the answer going in. You just have to do the math and get it here. Problem 3, I'll work it out either today or tomorrow, like next lecture. There's your solution. I don't want to work on Saturday night, you know. Okay, so we start here. R squared minus nu squared equal to 0. R equals plus minus nu. Assuming nu is positive, we'll write R1 equal to nu. Okay? So if that is the case, what is your solution? one of the basis functions is, so this would be case 1, where we still don't know if it's an integer, and we'll assume r1 minus r2 is not equal to integer. Or in other words, we'll just say new is not an integer. What is your basis function in this case? It would be y1 of x is x power r, in this case x power new, summation 0 to infinity am x power m. That's your basis function. You already know new. You have to get relations for a1, a1, a0, a1, etc. Yes.
Even if new is 0.5, it will give us an integer.
Should be a half.
Right. So I guess we'll just start. Okay. Instead of worrying about which case this is, in all of your cases, you would notice that this is one of the basis functions. This is always the basis functions. The other basis function is the one that changes depending on the case. So let's start with y1, okay, and see what we are going to get. So what do you do next? Substitute it in the original Bessel equation, right? That's the so we have x squared y double prime plus xy prime plus x squared minus mu squared times y equal to 0. Can you do this exercise like quietly and then look up? I'm also going to try. For those who can already see the answer, just bear with us for a couple of minutes. So I wrote down the terms that I'm going to need. I wrote them down, and I then factored out x power nu from everything.
The last one is m plus 2. Amx to the m plus 2.
Right. Thank you. So I factored out x power nu from everything. So when I substitute these terms into my Bessel's equation, x power nu will be present in every term. And we also already know that nu is a finite real number. So there is no way that x power nu can be 0. So we drop that out and then say comparing the coefficients of x power m on both sides. The way this statement is written is actually pretty general, where if, for example, if I had some arbitrary function s of x on this side, I would still have a power series representation of that, and this statement would still hold. Instead of saying, let me equate it to 0, which always may not be the case. Okay? Okay, I'll just directly go for x power m. Okay, let's gather the coefficients of x power m. Please do that and then look up. We'll compare our answers. Wait, no. I completely goofed this up. Not completely. And then I have minus mu squared y. So I'll have to write minus mu squared am minus 2 equal to 0. The rest of it is okay.
How did you get the first one? Yes, good.
First one. Oh, wait. I've been looking at the wrong thing. See, I told you I'm not that good. I should have been looking at this one. Okay, let's. I'm going to start over. Okay. All right. I have this first term. I'm seeking x power m, so I would have m plus nu minus 1 times am. This is x squared y double prime plus I need xy prime, which is here. I will have m plus nu times am, so that is xy prime, and then I will have x squared y, which is down here. I will have am minus 2, and then I'll have minus nu squared y minus nu squared y minus nu squared. Wait, am. Nu squared am equal to 0 equal to 0.
So you don't have to like bracket x to the power mean.
Yeah, we already made that argument. That x power, if you want, we can write x power nu is in 0. If you want to remind yourself. So this is a relation that connects am and 2 steps prior, am minus 2. Okay, so let's gather the terms. I have am times m plus nu times m plus nu minus 1 plus m plus nu minus nu squared. And then I have plus am minus 2 equal to 0. I'm going to do an index shifting where I'm going to replace m with m plus 2 so that I can write this as am plus 2 and this as am. That would be okay, right? Just shifting the index 2 steps to the right. So I would have am plus 2 equal to minus am divided by this denominator, which is, there I see some potential for cancellations, maybe, no, maybe not. So I have m plus nu times m plus nu minus 1 plus 1 minus nu squared which is am plus 2 is minus am divided by m plus nu whole squared minus nu squared, which is minus am m times m plus 2 nu.
When you do the shifting forward to AM plus 2, you don't have to change.
Oh yeah. Sorry. So wherever m appears, replace it with m plus 2. So that would be m plus 2 plus nu times m plus 1, m plus 2 minus 1, which is m plus 1 plus nu plus m plus 2 plus nu minus nu squared. Thank you, I missed that. So can we still do some factorization? Minus am divided by, so this m plus 2 plus nu appears twice, so I would still have m plus 2 plus nu whole squared minus nu squared. If I had any brains, I would have just done that by looking at m plus nu whole squared and replace m with m plus 2. All right, so this connects values that are 2 steps removed, which means if m equals 0, this will connect A2 in terms of A1. Okay, let's write this one more step simplified, which is minus am m plus 2 times m plus 2 plus 2 nu. So this will connect A2 with A0, saying 2 times 2 plus 2 nu, or this is minus A0 2 squared times 1 plus nu. What about A1? What about A1, A3, A5, and so on? How do we figure that out? Sorry? In terms of,
A1.
so if you start with this recursion formula, if the lowest value of m that you are allowed to take, which is 0, you are going to be writing down all the even values. So we have to treat the odd values outside of this formula. We have to do a separate treatment where, let's say, we look at m equals 1 separately and then see what clues we get from there. It's going to be a big simplification, spoiler. So what about m equals 1? So if you take this equation right here, you take this equation, this is 2 steps removed. You can set m equals 3. So this will be A3, this will be A1. Let's see what happens here. So if I set m equals 3, I'll have A3 times 3 plus new, 2 plus new, plus 3 plus new minus new squared equals A1 or minus A1.
Can't you just use the A equals 2 that we have?
Yeah, it will initially come in this, I guess.
Oh yeah. So if I set m equals 1 there, if I set, take this equation, this is minus A1 divided by 3 plus new, I can just use this one here, 3 times 3 plus 2 new. But what about A1? Itself. Sorry?
A naught and A1 might be unknown boundary.
No, we haven't written down. Okay. If you take this equation or take these series, collect the powers of x power 1 and let's see what happens. Let's see what happens if you collect the powers of just x power 1 from these summations. Okay? Can we do that? So collect the coefficients or equate the coefficient of specifically x power 1 on both sides. X power 1. So if I'm going to go look for that, that would be what? For x squared y double prime, what do I get? X squared y double prime, I need x power 1. So that's going to be m equals 1. So I have 1 plus new times new plus xy prime, xy prime
Isn't there an A1 with the coefficient in the first term?
plus, yeah, times a1 plus 1 plus new times a1. And then I have plus x squared y plus x squared y. Remember, indexing starts at 0. So what is the x power 1 power? Doesn't exist, right? So this term doesn't have a power x. And then I have minus new squared y, minus new squared y, which is new squared a1 equal to 0. Okay. If you do this kind of in a rush, you would conclude that a1 is 0, right? But let's also check the other terms. You have 1 plus nu times nu plus 1 plus nu minus nu squared times A1 is 0. So you have nu squared plus nu plus 1 plus nu minus nu squared times A1 is 0. 2 nu plus 1 times A1 is 0. If nu happens to be minus half, we are in a different world. But otherwise, we can conclude A1 is 0.
When nu is equal to minus half, it will be case 3, I guess. Because,
Minus half?
Yeah, because it will be case 3 because R2 minus R1 would be an integer.
So we are right for now excluding that to get A1 to be 0, which automatically implies all odd coefficients are going to be 0. A5, A3, everything else is going to be 0. So this recursion here, AM plus 2 and AM, if I may write here, this recursion AM plus 2 is 0 if M is odd and non-zero for M equals, let's say, 2k, where k is 0, 1, 2, and so on. Okay, like we did for Legendre polynomial, this recursion is going to be the basis of what will eventually be recognized as Bessel's function. Okay, so we'll stop here so that we can pick up from this recursion formula from the next lecture. Any questions about your exam? Like, is there anything that you think if I can do, it might be helpful? I'm willing to meet with you. I can post one more mock exam if that would help. Not a problem to make one more exam. What else can I do? Give an easy exam. I can always do that. I'll try. No promises.
Yes, another mock exam would be great.
I'll do that. I can do that by Thursday. Okay.
We left some portions of the first chapter for self-study.
Yeah.
Might we see questions from those parts?
So as far as the first chapter is concerned, I have reduced it to basically one word problem involving Bernoulli's equation. So when it comes to your project, it's going to test you on Bessel's function of second kind. And first unit is sort of like, it's tested in multiple places, so I don't have to separately test you on that. Okay, so maybe I can spend 1 minute going over the template. One second. So these are the sections that we covered. So chapter 1, it's reduced to one word problem, which is typically like a population growth problem or some kind of a kinetics or heat transfer, some kind of decay problem. Okay. Chapter 2, problem to solve a second order ODE using the methods of chapter 2. It's going to be an equation with constant coefficients, either exponential solutions, sinusoidal solutions, or xe power x type of solutions. So the first two problems are really giveaway. These are really two easy questions. They are equally worth as the third and fourth problem. So if I'm strategizing, I look at 80 minutes. I will try to save time on number 1 and 2 because it's going to get you points and in less time. Problem 3 is going to be proving an identity either involving Legendre polynomials or Bessel functions. So for that, you could prepare by going to these sections and doing the problems, as well as write down the Legendre's polynomial, write down the Bessel's function. Make sure if you can write, if I ask you suddenly write down P4 of x or calculate the derivative of P4 of x, see if you can do that. You should be able to write down the power series and be able to differentiate it or do simple operations with it. Differentiation, multiplication, integration, and so on. Problem 4 is going to be either power series method or Frobenius method. Okay, again, practice those problems, and I won't throw any curveballs. I am trying to look for competence, like whether you understood the material. Not like an advanced, the advanced testing is actually happening through your project. The first project is to get you into the groove of writing code. And the second project is where I really want to test your creativity, whether you are able to look at engineering problems and use the techniques in this class to solve those problems. Okay, so in this exam, just basic competence, nothing extraordinary.
So, nothing from chapter 3 and 4.
No, chapter 3 and 4, I already told you that's for your understanding as you go out as practicing engineers. Some people learn, some people don't. I get paid either way. Okay. Okay. Time is up. We'll meet on Thursday. I'll post one more mock exam. Thank you.